right, today we're going to do two things. We're going to go over some of the history of concrete and then take a break, and then we'll come back and we'll do a little design work with it. Now keep in mind when we're dealing with concrete, there's a couple nice things about this product that we use and makes it exceptional for structural work. In essence, one, it is great for compressive strength. In fact, it's not quite as strong as steel in compression, but it's fairly close. Two other elements that really bring concrete to the top on choice of a material when coming into some scenario that we decide to go with. Number one, you do not have to protect concrete from the elements. Okay, that's huge. Okay, so it can be on an exterior setting. Second thing, and this is maybe the greatest thing of it, because when you look at all of these materials we're going to deal with, this is the only one that does it. You can bring it to the job site in a liquid form and have it take any shape that you wish it to take. Okay? And that's giant when we're trying to make certain things mesh together, specifically meshing with the ground. Okay? So those are a couple big reasons. Before we jump into it, let's kind of look at a little bit of history of concrete and how it's been used in the past and where it came from. As far as we know, the Roman civilization started using concrete. And when they did it, I'm just going to push up here. Here's the material. So if you're in your kitchen cooking, Cheryl, it's probably you. You seem to get into a lot of little chemistry projects. When you're making concrete, it's made out of silica, lime, and clay. So silica, lime, and clay. Now the silica, which is sand, right, glass, same material we use for your glasses, we heat it up and it makes that. This is really kind of just a backer, it's a stable device in there. The lime is an acidic device and it will react with water. And then you also need the clay for when we cook it, it turns it in and gets a good mixture on it. So silica, lime, and clay. What they basically do is they crush it, make it into a powder, and then dry it. So you'll run it through some burners. If you go to a plant, there's a big one outside of Baker City in Oregon. I think probably a lot of you have driven by that, right? When we bring it to the site, or in a batch plant, we then add water to it. The water reacts with the lime, and it creates a hardened mass. So in essence, a couple things need to happen. One, you have to have a really good mix on this mixture, and you have to mix water thoroughly with it so that all of it is exposed to water. The chemical reaction that occurs takes quite a while to fully develop. And in fact, it probably never fully develops in some situations. But as a typical rule, we want that concrete full strength at 28 days or 1 month. Now certainly they do talk about where you have tons of concrete done, that some of it is never going to settle. You know, kind of the big ones like the Hoover Dam. Okay, there's actually concrete in the middle of the Hoover Dam, which was done 100 years ago, that still is liquid. Okay, in the middle of all that, they've poured so much into it. And it's just getting harder and harder and harder over time as that water hydrates and seeps out through the other pores.
So that was on purpose, they did it that way?
No, it's just so thick that the water hasn't migrated out from the back. Because you got to get that chemical reaction, and then it's got to off gas, right? And if it can't off gas, then it sits in a stable state. So in essence, it just keeps getting stronger and stronger.
And the heat is what helps make that water leave, or?
No, heat's just a byproduct of the chemical reaction. Because whenever you have that, you lose some energy and heat. And that's going off of it, but it's more the fact that the water cannot migrate out. Okay, because it's got to fully finish, and for it to do that, it's just got to leave. Okay? And it's so thick that it can't get out. Okay? Don't let that confuse you. It's just kind of an interesting fact that I've read, and that always kind of amazed me. Okay? But of course, that thing had a lot of concrete in it, right? Yeah, I think it is still, in today's world, I think it's the third biggest pour ever done. I know there was a hotel in Las Vegas That was done a couple years ago. They took over the new #1 spot, where they poured continuous for 28 days on that as trucks coming. I can't remember the ungodly amount of concrete they poured on that thing, but it was a lot. So in essence, keep in mind, we're basically looking at lime hydrating with water, and then we have silica and clay, and this is called concrete. Concrete. Now I'm going to get kind of specific on 3 terms, and we use that to define concrete and other additives that we've added to it. So concrete is these materials right here. We call it Portland cement because it looks like a quarry over in England that produced stone that look just like this. Now, you probably have heard about the Roman aqueducts and stuff that were poured 2,000–3,000 years ago that are still functioning today with no upkeep on them at all. So it's a very long-lasting product. It'll certainly last longer than all of us when we use it in a structure. So that's another nice thing about it. Any questions so far? There's a guy.
You call concrete Portland?
Portland cement.
I've never heard that.
Yeah, it's actually called cement. Now we call it Portland cement, but most times if you look on a bag today, it'll say cement only. Okay. A guy named Joseph Aspdin in 1824 is the one that patented this process. Okay. That, of course, is long expired, okay, so everybody can use it all over. Now, what happens when we get into more of how we get this stuff stronger? Because we're dealing with a powder, right, that hardens into a mass. And it really is only capable of certain strengths. So what we end up doing to make it stronger is we put aggregate in. By aggregate, we are adding rock as a general rule. When we add this rock, we have to make sure it's a stable rock, right? It can't have any lime in it. It can't have any calcium in it, because what's then going to happen? It's going to react with the lime and the rock's going to eat itself up. And so we always use some stable type, usually a quartz or a granite type of rock. Believe it or not, the aggregate, I put in here at 75% of the volume for the most part. This is the strength component. The rock is much stronger than the cement. So the cement up here, this is the weak part, but we're going to add it to it. When we have cement and we add aggregate to it or rock, we call it concrete. So cement's just the material. Concrete is cement with rock added. Now the rock you put into it will vary depending on what you want the concrete to do. If you want it to be very strong, we'll use larger rock. And the way we basically do that is we'll call it out as say, we're going to get cement with 3/4 minus aggregate. Has anybody heard that term before? Juan, you've been a little bit in mining. You ever heard that? Okay. Any soil work, anybody? Okay, so if I call out a 3/4 minus, what am I calling out as far as the rock? Let me just kind of show you. Because we run rock through a crusher, right? And it doesn't come in uniform size. And so what we do is we end up having a screen. Okay? And we got a bunch of different types. But what we'll do on this screen is we'll say that distance right there is 0.75 inches. And so we just crush a whole bunch of rock, run it up a conveyor, and then run it across the screen. Anything that falls through that screen is 3/4 minus. Anything that vibrates off the end of it and doesn't fall through the screen is too big. It goes back around through the crusher. So we always call it by that. We call it a pea gravel, which is a very small, like 1/16 inch. And you can call it 1/2 inch, 3/4 minus, whatever the case might be. The bigger it is, the stronger it is, up to a point. Now, certainly, I don't know that we would really call concrete, like most of you have been through Old Town here or Shoshone. Shoshone's a classic one. When you're driving down the highway through Shoshone, you see a lot of houses with lava rock foundations, and they're mortared in, right? Well, they're more dealing with cement. Technically, that's concrete, although their aggregate is 3 feet big. I don't know if you could really call that concrete, right? That's more of just a mortared brick wall. But certainly, we don't want to get too big to where we get real weak seams on real hard stuff, create those shear spots. Any questions on this? Now, I'm going to pass something around so you can kind of see this as we go through it. I think I've sent this around before. This is a core sample out of a slab. This is the rough side's the bottom that was sitting against the ground, and we drilled this out. You'll see the aggregate in here, and you'll also see the cement, which is the grayer stuff that looks like that. And if you look closely and you get it in the light, you're going to see a couple shiny areas. Let me see if I can put them on here. Glasses can see. It's got a little bit of welded wire mesh in it, and it's in the top part. Let me try to find one. Of course, now I can't find it. Oh, there it is, right there. I'll put a Sharpie mark on it. So there's that one. And you got it coming out the back too. Okay, so there's a little bit of metal in the bottom of this. So this is really not cement or concrete. This is reinforced concrete, okay, where we add metal to it. And I went and there's little white out marks in my black pen on it, if you want to look at this. So you can kind of see how concrete sets up. So that kind of brings me to my next line on the notes. When we add steel or another material, we call it reinforced concrete. Where the concrete means that it's cement plus aggregate, and then reinforced means we're adding another material to take care of it. Now, why would we add another material if this stuff's so great and wonderful? Because it's not great and wonderful. It has a glaring default in that it is terrible in tension. Okay, pulling apart, it's terrible. All rock is. Okay. In fact, just, another kind of nice fact. I did a lot of blasting in mining, so I blow stuff up. Loved it. Got paid a huge amount of money to go blow stuff up in the sand pit. Okay, that's a pretty cool thing. But anyway, when we blew up rock, you don't break it with the explosion. Okay, the explosion actually compresses the rock, and then as the gas from the explosion leaves the hole, the rock comes back into that hole and goes into tension. That's when the rock breaks. Okay, so when you see an explosion, it's not breaking during the explosion, it's breaking after. Okay, and this stuff's the same way. Okay, so in essence, if I'm sitting on the ground, let me just draw a quick footing. Let's say here's my soil horizon. I come in and I pour a long footing on here. That's concrete. Now over time, I might get a place in here where that soil underneath that slab settles. Now I've got a weight going on here, let's say of a house. Okay, so it's a continuous weight, right? There's my free body diagram. So I'm hitting that. What's going to happen right here in this situation where that soil is settled out underneath my concrete? Okay, it's terrible in tension. In fact, it's so bad in tension we don't even calculate. Well, what's going to happen is you're going to start getting a crack migrating up through here, right? And if that crack ever gets all the way through, then it might basically ruin the whole thing, right? So we got to be careful of that. How do we stop this from happening? Because we can't see underneath here. Well, we can't really stop this from happening. It's going to happen. What we do is we add steel to it. Steel and concrete are like a long-term marriage. First sight, you're married and you make your 1,000th anniversary. These two are absolutely perfect to work with each other. Steel, its strength is tension. So we added in there, so I kind of drew a quick picture. So we're putting some weight. Top of the slab goes into compression, right? Or the beam, whatever the case might be. The bottom half has to go in tension. That's where that crack's going to occur. We put steel right in this lower part. So we know this crack's going to start, like right there, but it's going to then hit that steel. The steel will then stop it and carry that weight. And it's really kind of neat when you look at it, because at 0.03 inches of deflection is where concrete starts to break. So at 300ths, if you get that thing to deflect down 300ths, it'll start to break. Guess where steel is its strongest? 300ths of deflection. That's when it reaches its maximum value. So the two work perfect for each other. That's why we add it. Okay? So most of the time, we're putting steel in here in the form of rebar, right? Now, we're getting some new products. I've got on here fiberglass, steel screws, wire. We're trying to work stuff out. In fact, we're going to use it today in our slabs. We're going to add a product called Fortifiber. And in essence, it's a plastic fiber that has been fiberglass reinforced, and it's starting to take the place of rebar. Because you get millions of these little pieces of fiberglass in there that will then do it. It won't replace rebar, but there are people working on how to get it to where they can. They're starting to put metal shavings in it. They're starting to just take wire and wind it through it so that you can then get away from this rebar tying that we do. Okay? And just have it injected in the mix when it's put together. Now, the fiberglass, it works okay, but it's not as strong as rebar. The problem you get with it when you finish like a slab, like we're walking on a concrete slab right here, right? And you're out in the hallway. You see how smooth it is? If that has fiberglass in it, those little strands are sticking up in there and it's hard to finish the floor. You have to use basically one of those walk-behind buffer type concrete machines. And then they'll shear that stuff off and you can't do it by hand. The problem they're having with these steel screws, Purdue University I know has been working on this for a long time. You can't use it in slabs because that stuff just doesn't shear off. And so your slab's got a bunch of little pieces of metal sticking out of the top of it, which is fairly hard on bare feet. Okay, so kind of like walking across your nails. But they're working on it. And the whole point being, let's try and make this a little easier to get away from rebar. Mostly you want to think of this stuff as just aesthetic crack control. When we really need the concrete to perform, we're going to rebar. Okay. Any questions on this? Yes.
So that's mainly used like when you do countertops and stuff?
Yes. Uh-huh.
Okay.
Yeah, and you
But
can
you
put it in
don't
a...
have so much compression.
Right, if you're sure that slab or item will stay in compression, then you can go use this stuff. It's whenever that slab's gonna hit tension, that's a different story. So if we know, like your driveways don't have rebar in them. Okay, but it's a big slab, it's 4 inches, that will carry the weight of a car, goes in there and does just fine, right? If you get a little crack in it, hey, who cares? We just keep driving over the crack. Okay, but still doing what it's supposed to do. Okay, so it's just that when you use it for a structural sense, that we really got to be careful of this. Okay. So there's a difference there. A slab like a floor, which is a platform for occupant use, we talked about that yesterday, that's not really a structural item, right? It's the joists and the decking that are the structural items. Does that kind of make sense?
What's the advantage to making a bridge out of concrete, like we dropped the eggs off of, or like the prime bridge?
Which is made out of steel?
Yeah, like why would somebody want to do one over the other?
Good question, because they're done with both materials. But there are a lot of things that come into play. Can you pour it, for one? Can you pour concrete? Prime Bridge is a unique situation where we have, what is that thing, 1,000 feet approximately across. So how would they build the formwork for it? In essence, it's next to impossible. They have to build the structure for the formwork, pour the concrete, and then remove that entire structure, right? So a decision was made on that case to go with steel, because they can just go ahead and bolt it all in place. Now, certainly, there's bridges out there that are just as long as a prime bridge that are all concrete. Usually they're in a suspension type of arena. Think of the Golden Gate Bridge, it's kind of a combo. That's a big one. I think the Oakland Bay Bridge has a lot of metal in it, but it's got a ton of concrete in it also. Some of these really big ones. John, you want to say something?
I was going to bring something up about the Golden Gate Bridge when we were talking about deflection. Do you know what they used, what they added into concrete to make the Golden Gate Bridge? They used rebar?
Yes.
Okay.
Yeah, and I've never seen the drawings of it, but I know a guy who worked on it. Daryl Patron, one of our local inspectors. He cut his teeth back when he was a young man working on that project. We talked about it one day. That's from his mouth. But yeah, there's big rebar in it. I want to think he said he used a number 9 or a number 10 bar, enough they couldn't lift it.
Okay. Because I remember when they had a big party on the bridge to celebrate however many years ago it was built, and they said they had survey equipment set up, and like during the kind of middle of the party, they surveyed the bridge, and the whole bridge had dropped 6 feet because of all the weight.
Yeah, I wouldn't doubt it. Now that one's long enough to where the deflection's not going to tear it apart, right? Because if it's 6 feet there, it's all a function of distance, right? You're gonna see. This might be it's something you're going to see again. We are held by code for deflection to be equal to length divided by 240. That's the maximum deflection we will allow on anything. And so in essence, you take your length of something, divide it by 240, and that gives you maximum deflection. So if we have something that's 1,000 feet long, obviously we're going to allow more deflection, right? As opposed to something that's 10 feet long. But if that's 10 feet, 10 divided by 240 would be what, 0.24? Okay, so on a 10-foot device, we're going to allow about 1/4 inch of deflection on the whole thing, maximum. 1,000 feet, that would be 24. Okay? And it's still going to hold together.
Is that what went wrong with that famous waving bridge?
Galloping Gertie?
That had more to do with resonance.
That was residents in Tacoma. Yeah. Yeah, that's a famous one. If you haven't ever watched that video, YouTube it. Galloping Gertie, I think is the name.
Yeah.
It's pretty impressive what the wind can do there, isn't it?
Mhm.
Yeah.
So that none of this came into.
I think that was actually a steel suspension bridge. The platform they drove on was asphalt, but I think it was steel suspension.
It's been a long time since I saw it. Too.
Yeah. Yeah. Certainly, we learn a lot from that stuff. We learn a lot from that when that happens. In fact, once that happened, we changed all how we do bridges once that bridge went. Yeah, it's started to come back to me too, because a long time I watched it. It actually, do you remember where it catapulted those cars? I mean, they're just flat flying through the air off of that thing. Like some giant picked them up and had his tinker toys and throwing them.
Well, it wasn't like it was new either. It had been doing it for, since, I think it only lived about 6 months, but I think from day one it was very wavy.
All right, let's get back to some more of this stuff. Your strength is amount of Portland cement water ratio. So the more, obviously, that we add, the stronger it's going to get. Keep in mind, the reason I mentioned this is how we spec out concrete. So we call out concrete at 3,500 PSI, which is real standard for your houses on exterior concrete. That's probably what you have in there on your driveway. Is 3,500 PSI, so which means that it will hold up 3,500 pounds on 1 square inch. That is the weak part. That is the cement. The aggregate you put in there is much stronger than that. The rock we add to this stuff is upwards of 40,000, 50,000 PSI. So here's what concrete companies are held to when you order stuff. Many of you might get into as a drafter. A lot of times we're taking these concrete samples. We're out on the trucks when they're pouring bridges and taking these and testing them. 14 days it has to be at 80% strength. 28 days it has to be at full strength. So typically, concrete companies, to protect themselves, if I order 5,000 PSI concrete, they're probably shipping me 6. Because if I take that and test it and it doesn't meet these requirements, the concrete company is responsible for tearing out and replacing it. We actually had a concrete company in Twin go bankrupt about a decade ago because of this. I don't know if you folks remember when they redid Full Line through the Costco, Winco area. That first bridge you come over that has the pass underneath it for the walking trail, that's been built twice. The first time they built it, one of our concrete companies that supplied it, the concrete didn't meet spec. They ended up having to rip the entire thing out and replace it. What's that?
Which part of it?
The entire bridge. The abutments were supposed to be something like 10,000 PSI and they came up to 8. In essence, that company went under on that project. They screwed up on their batch plan. But anyway, be that as it may, that's what we need to kind of watch out for. Okay, let's kind of look at how we use some different concrete. Okay, we use it for basically everything. First off, let's look at it in a beam situation.